In this video, we prove a theorem stated a while back, and that's the following. If G is a group, and if H is a normal subgroup of G, then we can turn G mod H, which is the set of cosets of H, into a group by defining a binary operation star on G mod H by taking two cosets with representatives A and B, and then all you simply do is multiply the representatives A and B using the group operation in the group G. And then A times B, H will be the coset that is the product of these two cosets. So what's crucial here is that the group H is normal. So the subtlety of this result is that we need to show that this rule that we've defined of multiplication of two cosets is well defined, because as written, it depends on the names or representatives that we've chosen for these two cosets. Remember, AH is, as a set, it consists of a bunch of elements, and A is one of those elements. Similarly, BH is a coset, so it consists of a bunch of elements, and B is one of those elements. And then we take an element from this coset, an element from this coset, and multiply those elements in G, and we get an element in G. And we say that, well, the coset that that element is in is the product of these two things. And so the question is, or the issue is, what if we choose different representatives? So for example, if A1 and A2 are elements of G, so that A1H equals A2H, and similarly B1 and B2 are elements of G such that the coset B1H equals B2H. Again, this does not mean that B1 equals B2. It could, but generally it won't. Then what we need to make sure is that A1 B1H equals A2 B2H. Then this definition will be well defined, meaning it doesn't depend on choice of representatives that you chose. And that's very important for this definition to be an acceptable definition. The proof is actually quite simple if we use the following characterization of normal subgroup. It's the one that our book uses actually. It's that G, subgroup H is normal if and only if G times H equals H times G. This left coset equals this right coset for all elements of the group G. Okay, so using the fact that H is normal, so we start with what we want to show is A1 B1H equals A2 B2H. So let's start with A1 B1H, and our assumption is that B1H equals B2H. In other words, B1 and B2 are different names for the same coset. And so B1H equals B2H. Now, because H is normal, we can move this H past the B2. And so we get this A1 A1H B2. And then because A1H is the same as A2H, that's again by our assumption that A1 and A2 are different names for the same coset. We go from here to here. And then we move this H back over, again using the fact that H is normal. So that's why we can do that. And so then we're done with the proof. We've got A1 B1H. The set is equal to A2 B2H. Finally, let's prove this following fact, which says, let H be a normal subgroup of a group G. Then the map that's given by G to G mod H, sending an element G of our group to the coset GH, is a homomorphism with kernel equal to H. The point of this theorem is saying that every normal subgroup is the kernel of a group homomorphism, of some group homomorphism. And this is reminiscent, or the converse, of an earlier fact we've seen, that the kernel of any group homomorphism is a normal subgroup. This is saying that if you have a normal subgroup, it is the kernel of some group homomorphism, namely this group homomorphism. Okay, so the proof is quite simple actually. The difficulty was making sure this is a group. Since H is normal, this G mod H is indeed a group. Okay, so for phi to be a homomorphism, what that means is phi of G1 times G2 equals phi of g1 times phi of g2. And well, on the left-hand side here, we've got g1, g2h, since that's what phi does. It sends an element to that element times h, so to this coset. And we're wondering, is that equal to phi of g1 times phi of g2? Well, phi of g1 is this coset g1h. Phi of g2 is this coset g2h. And so on the right here, we're multiplying two cosets. And the definition, that was the star operation for the multiplication on g mod h, is you simply multiply the representatives. Whatever the representatives you have, multiply them. g1 and g2 are representatives, and we multiply them, and that we get g1, g2 times h. Okay, so we've checked that phi is a homomorphism. And then to establish this second fact that the kernel of phi is h, so the kernel of a homomorphism is, by definition, the elements that are mapped to the identity element in the target. So the elements of G, so that GH, that's what phi of G is equal to H, because H is the identity element in G mod H. And so this set here is H because, well, if you've got a G, so that GH is H, then G times the identity element is an element of GH because the identity element is an element of H. And now, since we're assuming GH equals H, what we get is that G is an element of H. That's what I've written here. And so we get that the kernel of phi is H. I mean, here what I've shown is that the kernel of phi is a subset of H, but showing that phi maps H to H follows from H times H being equal to H, since H is a subgroup.